Well, hello. Welcome to class 20. And in looking over your project proposals and what you're working on, I notice it's some of you, it's important to understand how to do collision tests for some of the stuff that's going on in your games. And while today is not going to be a complete coverage of the topic, we're going to talk about enough that I think it should work for most of the projects you're working on. So let's get started with that. So collision tests for games is what we're going to be covering. So let's go ahead and get started here. All right, so the first thing is that in game programming, there are a lot of cases where we need to see if game objects are colliding with something. Maybe colliding with each other, colliding with something in the geometry of the world. And some examples might be, is the player colliding with the ground or the wall? In other words, are they standing on the ground? Did they run into a wall? Is a bullet colliding with a player or an enemy in the game? Is the end of some melee weapon that's being swung hitting an opponent? Is the character within some blast radius collision sphere, collision circle of an explosion? Is the player standing within some trigger area that causes a gate to open or the level to be considered complete, or a teleport area or whatever? Is an object within the visible view of the window? Is it colliding with that window? So do we need to display it or not? And so because of that, we may need several types of collision tests and different types depending on what the situation is. And so today we're going to look at several types of collision tests, and we're going to look at points, circles, and rectangles today. Notice that there are collision tests for other things like triangles. Is this triangle colliding with this other triangle? Is this circle colliding with this line? So lines, triangles, and then really arbitrary polygon shapes, other than what we're going to talk about today. And so today we're going to look at a few of these: point, circles, point, rectangle. And so sometimes you need to know differing types. Is this circle colliding with this line? Is this line hitting this polygon, and so forth? So we're going to look at these simple ones today, including tests between those types. And then maybe at a future point, if it turns out I think it's necessary for your projects, we might look at some more complicated collision types like line segment with line segment with circle, a triangle with another triangle, arbitrary polygon with arbitrary polygon, and so forth. But I am going to present at the end of this lecture today a way that you can use these simple ones to still handle more complex geometry. Okay, so point-to-point collisions, let's start with that. And that one is actually pretty easy, although there's a little bit of subtlety here we'll see. So for example, if we say, do it in this kind of naive way where we say, okay, I'm going to pass in the coordinates of the 2 points, x1, y1, x2, y2. So that's 2 different points. We want to see, are those colliding with each other? Are those points in the same space? And the naive approach would be to say, well, if x1 equal x2 and y1 equal y2, then we return true. Otherwise, we return false. But you may notice a potential problem with that. Imagine that x1 and y1 and x2 and y2 are not integers, but they're floats. And so the problem here is that that method will only work reliably if the coordinate values are integers, because they could be floating point values, and you could have like 1.0 and 1.000000001. And while those would technically be occupying the same space on the screen, it might not be detected as a collision, and it might never be detected as a collision depending on how far they're being moved each time. And so we might want to come up with a more reliable way of doing that that's not just doing the double equal comparison. So one thing you might think is, well, let's just cast those into integers. So we just take an int of each of these and an int of each of those. And the int function in Python just truncates anything after the decimal place. And that will work a little bit better, but it still might not be great. So for example, point 1.0 and 1.0 and 1.99 and 1.99 will collide, even though they're almost 1 apart in each of those things. But points 1.0, 1.0, and 0.999 and 0.9999, I think I left off a 9 there, don't collide because we're just truncating. So even though these 2 points are closer, they're not colliding. Even though these ones are farther apart, they are. So one way to improve upon this would be to do something along this. So here's another improvement where we would say, you know what, let's take the absolute value of the difference in those. And if that's less than 1, and the absolute value of the y's is less than 1, then we say that those are colliding. So in other words, we're saying if they're closer than 1 unit apart in both of the two axes, we're going to say they collide. Now that solution offers a much more uniform collision test. It's still very quick. It only has subtraction and a comparison in it. We're not doing any complicated math, and it'll still work with floating point values. And so that's actually a pretty good one for points. Now, we will see another way to do this here in a second after we talk about circles, but let's move on to circles. So circle to circle collision. We've got 2 circles. We want to see if they're colliding. Each circle has a center point, as you can see down here, and each circle has a radius, how big the circle is. So how do we tell if those are colliding? Well, the idea is to calculate the distance between the centers of the circle. So how far is it from the center of that one to the center of that one? But then what do? How do we know if they collide or not? And the quick answer to that is if that distance between the centers of that is less than the sum of the 2 radiuses. You can see there's the radius of the blue circle. Here's the radius of the green. If the total distance between the centers gets to be less than, or maybe you'd say less than or equal to. If it's equal to, they're just touching. If it's less than, then they're kind of overlapping a little bit. Then we know that they're colliding. Maybe I'd say is less than or equal to. It's more appropriate because that would be right where they're touching. But if that happens, would they have to be colliding? All right, let's write the code for that function. So the code for that function, def circle circle, x1, y1, r1. So there's the x, y, and radius of circle 1. Here's the x, y, and radius of circle 2. So what we're going to use is calculate the distance between the centers. So x2 minus x1 squared, y2 minus y1 squared. So again, this is just Pythagorean's theorem, using the difference in x, difference in y, to get the 2 legs of the triangle, squaring both of those, and then taking the square root of that to get the square root of the hypotenuse, or to get the hypotenuse from the square of the hypotenuse. So to take the square root, I'm just raising to the 1/2 power. And then what we do is we say, hey, if the distance is less than, in other words, if this distance is shorter than r1 plus r2, return true. Otherwise, return false. So one thing to note about this code, though, is it has a square root calculation, which can actually slow down our game, especially if we're doing a lot of circle-to-circle collision tests. So is there some way we could eliminate the square root on this? And the answer to that actually turns out to be, yeah, that notice what we're doing is we're taking the square root, and then we're comparing it to the sum of these 2 things. Well, if I didn't take the square root, I'd have the square of the distance squared, and I could compare that with the sum of these 2 things squared. So the solution to that is I just changed the variable name here, but just to leave off the square root and then check against radius 1 plus radius 2 squared, and that will give us the same comparison, but now we no longer have a square root calculation being done, and this can be done much more quickly because squaring this is just multiplying it by itself, which can be much faster than trying to go the other way and take a square root. So this is an improved implementation of the circle versus circle collision. And we've eliminated that square root. And notice we could also use this on a point-to-point collision by leaving off the radiuses. The radiuses in that case would be 0.5, but notice 0.5 plus 0.5 would be 1. 1 squared is still 1. So if you wanted to use this on a point-by-point basis, you'd pass in the 2 points, calculate the distance squared like we have here. And I don't know why the font screws up that Q there, but just pretend that's not like that. And then we just compare this. Hey, if the distance squared is less than 1, we know that the 2 things are colliding with each other as points. So that's where I mentioned earlier you could do it with a modified version of the circle collision as well. All right, we also have point circle collision. So the idea there, that's similar to a circle-circle test, but with one of the points having a radius of 0. So in other words, radius 1 plus radius 0 squared would just be the radius of the circle squared. So this is the same test with a point to circle test. So essentially it's a circle-circle test with a radius of 0 for this point. And the test becomes, is the point inside the radius of the circle or is it not? Okay, what about a point to rectangle collision? Here we want to see if the point is inside the rectangle. And to do that, what we're going to do is we're going to assume that this is an axis-aligned rectangle. In other words, this is the side it's not a tilted rectangle. There's a more complicated test we would have to do with that, which we might talk about in a future lecture. We won't talk about today. So we're just going to do axis-aligned rectangles for our tests today. So here's a rectangle. Is that point inside of it? Well, how can we tell? Well, if we think about that for a few minutes, I'll pause here and let you think about it for a couple minutes here, and then we'll write the code. Well, if the so let's go ahead and start. So if the x coordinate of this point is between the left side of this rectangle and the right side, and the y coordinate is below the top but above the bottom, if those four conditions are met, then that point has to be inside of that rectangle. So here's what the code looks like for that. We say if point x is greater than rectangle x and point x is less than rectangle x plus the rectangle width. In other words, if point x is bigger than this side and also less than the coordinate of that side, and point y is greater than the top and also less than the bottom, if all of those four, there's the four tests, 1, 2, 3, 4, if all of those are true, the point has to be inside the rectangle. We return true, otherwise we return false. And you may have used code like that to check mouse clicks on previous labs where you have to click in a box to exit the program. There were some bonus points given for doing stuff like that previously. So if you did that, then you may have implemented this before, but that's essentially what the idea is saying, are the coordinates of that point within the bounds of this rectangle, both along x and along y, and if it is, the point has to be inside of there. And notice I did less than or equal on this, so if you're on the edge, it still counts as in. Some implementations you might want to have on the edge not count as in, so you could change these to greater than and less than rather than greater than or equal to and less than or equal to. So the test here is the point within the dimensions of the box, and if it is, return true. Now, rectangle to rectangle collisions are a little more complex, but not too much so. And here we want to check to see, and here let me change it. It's supposed to say 2, not TO. Like 2 like the number. 2. Okay. So that we want to check two axis-aligned rectangles. And the idea is we want to see if the coordinate ranges overlap on both axes. In other words, if they're too far apart along the x, they can't overlap. If they're too far apart along the y, they can't overlap. So in other words, if we were to project across here, and there was a gap between the bounds of this rectangle and the bounds of that rectangle, they couldn't overlap. And the same thing would be true along the x. If we were to look at that and look at that, we could tell that they didn't overlap. Now, there's a number of ways to do this. One of them would be to say if we take the maximum x of one rectangle and the minimum x of the other one, and if the maximum of this one is less than the minimum of that one, then they can't overlap. But there's an easier way to do that because that has a lot of cases. Rectangle 1 could be on the left, it could be on the right. Rectangle 2 could be on the top or it could be on the bottom, and so you have to test that in all of those different cases. The way I like to think about this, and the way I'm going to implement it here today, is think about it kind of like the circle test. Think about the distance between the centers of those. But let's think about it along each axis. So let's think about the distance between the centers coordinates along the x. So if this distance here that we calculate from the center of rectangle 1 to the center of rectangle 2, if that is larger than the distance from the center to this, or half the width of that one plus half the width of that one, if this distance is larger than that, then the two rectangles have to be so far apart they could not overlap. If that distance is less than that, then they could overlap. And then we do the same thing in y, and if they are truly touching each other, then we have to be overlapped both in x and in Y to do that. So in other words, we're going to take the center of each, and if they are close enough to cause an overlap along both axes, X and Y axes, then the rectangles have to overlap. If it's not true for both axes, they cannot overlap because they're farther apart than they could be in one of the two axes. Let's look at the code. So the code is actually relatively simple. Basically, I calculate the center point for X for rectangle 1 for both X and Y, and I calculate the center point for both X and Y for rectangle 2. And then I take the absolute value, in other words, the length, the distance between the centers in X. And if that distance is less than or equal to the sum of the two widths divided by 2, in other words, you could just say rectangle 1 width divided by 2, rectangle 2 width divided by 2. I just factored out the 2 here. So if this is less than that, then it can overlap. And if it's doing that in both the x-axis and the y-axis, they have to be overlapping. So there we see that true. Otherwise, if that all isn't true, they cannot be overlapping. So we return false. So notice this is pretty simple, pretty straightforward. Also very high speed. I actually implemented this years ago on resource-constrained systems for games I made way back before computers were like supercomputers. And a cool thing about this is this divide by 2 that you do here, that can be done with a shift operation. So this can be made very fast. Rectangle-to-rectangle collision tests like this can be really fast with just a few CPU operations. Doesn't really matter so much in a language like Python running on a really fast machine, but if you want to implement something in C language and have hyper-fast comparisons, and you're writing code for a Nintendo NES, then you can implement this in a really fast way in hardware. But this is the algorithm that I've used, and it works really well, and it's really fast. Now, circle-rectangle collisions. This gets a little more complicated. And in this case, for that test, we need to determine if the circle and rectangle overlap. Now, the first thought might be imagine a box around the circle and just see if that overlaps. But you might notice that there are cases with that where the box around the circle would indicate an overlap where there was none. So what we're going to do is we're going to change that around a little bit and say we're going to test this rectangle versus that one, which we know we can do really fast using this algorithm. We're going to check that, but only if the center of the circle is within the bounds along the x-axis or along the y-axis. So if one of those two is true, if the bounds of the center are within the y-axis or within the x-axis, then we're going to test the square around the circle versus the rectangle. Now notice that if we're checking that bounds there, in this case, notice the center is probably to the right, so we wouldn't check the bounds, but it is within this way. So we're going to go and do that, and we're going to find that it collides. And we would do that if it was along the bounds. If the center of the circle was like right here, but the circle came up and touched that, if that's within the bounds of that and that, we check it and find out that the rectangle overlaps. And what that does is it puts the rectangle test first in most cases. And that's a really simple, again, really simple test to do. We just did that here very fast to do that. But there is a corner case that could miss, that we don't want to use that, and that's where the center of the circle is neither within this way nor within that way. In other words, the center of the circle might be down here, but it could still be colliding up there. And that corner case would look something like this. So if you look up here, you can see that happening right there, where the center is clearly beyond the maximum y, and it's clearly below the maximum y, beyond the maximum x, but it's still colliding. So how do we do that? In the case where it was not within the bounds this way or within the bounds that way, then we just check to see, do a point test to see is each or any of the four corners within the circle, and if they are, we return true. And if it fails all of those corner tests, we return false. So let's look at the code. Here's the code. A little more complex, but you'll notice that notice I built up this test using the other ones we had created earlier. So in other words, I say, hey, if it's within the range of X or it's within the range of Y, I just do the rectangle test. And that's either going to return a true or it's going to return a false. If it was not within the range, then I come down here to the else and I do the corner test. And there is a slightly more efficient version of this that I've used where I do one additional box test here, and if the box test returns true, then I check all the circles. And if the box test returns false, then I know it can't collide anyway, so I just return false. But this, I made it a little simpler here just to cut out that extra operation. But basically, I just say, hey, is the upper left corner within the circle? No. And then I go over to the next one. Is this corner within the circle? Is this corner within the circle? Is that one within the circle? And if any of those return yes or true, then I return true because that means it's on one of these four corners. If all of those fail, then I eventually pop down here and return false. And this test actually works really well. And what I would suggest you do, what I like to do is I like to create a collision test library where I have point, circle, point, point, circle, 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 rectangle, rectangle, rectangle. And then eventually you may need to add circle, line, triangle, 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 circle, and so forth. And then you can just call that up as a library of those different collision tests as needed. Now, for complex collisions, there are other kinds of tests we can do that are more complex, but in a lot of cases, the collision detection doesn't need to be exactly pixel perfect. It just needs to be an approximation because when you're playing a game, if you get too close to an enemy, then all that matters is it does damage. Or if you, and you may have noticed this in games where it looks like you kind of just went through the edge of something, but it didn't register as a collision. And the reason is a lot of times they'll come up with a collision test that has an approximating collision area. And so that could either be like a bounding collision rectangle, like you see around this Pac-Man Ghost here, or it might be a bounding collision circle, like we have here. And that rectangle that bounds some geometry is called an AABB, or an axis-aligned bounding box. And you'll see that used a lot in games. And the reason for that is if you think back to our rectangle-rectangle collision, super fast. You can do that really, really fast. So if you can get away with doing your collisions as some sort of bounding boxes around the geometry, then you should do that because that's going to speed up your entire game. There's also a technique where you can actually use the axis-aligned bounding box to say when things are not colliding, and then if it tests true, then you could do a more complex test inside of that, and that can save a lot of time too. Rather than doing the complex test every time, you say, well, this clearly isn't touching, it's not in the box, but if it is in the box, then you can say, all right, it's in the box, now I got to do the work to figure out is it really colliding or not by doing something more careful. So the rectangle collisions are probably going to be something you should spend a good bit of time on. Those are definitely your friend if you can get away with it. And some geometry, circles are helpful, but notice the circle had a little more mathematical operations there with squares being involved. Even when we didn't use the square root, or we just used the squared term, still a little more math being done there, but still pretty fast. So if you can get by with a circle or a bounding box that's axis aligned, go for it. Now, another thing that you can get away with if you have a complex collision shape is you have some character you want to know, maybe did parts of this. You don't want to make a box that goes around this whole thing and have something hit the air up here and have it register as a hit. And then the other thing that you can do like this is you might want to know where the collision happens. You might want to know, did Mario punch something, or did his feet hit the ground, or did the bullet hit, not that they're, I guess, bullets much, or was the bullet a headshot, or did it shoot him in the shoulder? Does it need to do something in that to blow back his torso? Whatever. I guess I just invented a first-person Mario shooter game there. But anyway, in those cases, you can actually have one object have multiple collision shapes. In other words, over here, notice I have a rectangle on the torso, rectangles on the legs, and then circles on the 2 feet, circles on the hands, and then a larger circle on the head. And this geometry like this can now do a pretty good job of not just detecting collision with hands or feet or which part of the body, but it can also be used to have those parts of the body interact differently. In other words, if you want to have the hands be able to grab onto things, you would then have to detect collision with those hands, which is where circles around the hand parts of the geometry would work. And if you've played a game, there's a really fun game called Heave Ho, where you have these little characters and they have to grab onto things and swing around and work cooperatively to solve these levels. You need to do that collision with the actual hand and distinguish between left hand versus right hand in order for a game like that to work. And so using a collection of simple shapes like that can often be better than doing some pixel perfect thing like that. There's still approximation of the collision, but a lot of times that's going to end up being good enough and fast so your game can get away with it. Now, for more complex collision types, we're not going to get into these today, but there are collision tests for a line segment versus another line segment. In other words, if you have two line segments, knowing are they overlapping or are they not? Are they just near each other? And there are several ways to do line-line collision tests. We're not going to cover them here today. I like a parametric version of that. There's also a circle line that you can do, and that one uses vectors and a dot product, and then to get the normal between the thing, and then if the normal distance of the orthogonal normal from the line to the center of the circle is smaller than the radius, you know those two things are colliding. I think you may have talked about these in the 1803 class. Presumably you have, but things like dot product, cross product can be useful for those. But that circle line test could be quite useful. Also, triangle circle test is a circle colliding with a triangle. And one of the ones that gets used a whole lot is triangle triangle. And the triangle triangle one can act that methodology, that algorithm, which is called SAT, or the separating axis theorem. We may look at that in a future lecture. But that one is also can be implemented really pretty quickly, and it can be extended to not just triangles, but any kind of arbitrary polygons, including polygons at any angle. So in other words, rather than having axis-aligned bounding boxes, you can do like squares that are sideways, or a triangle and a square, or as long as the objects are polygons that don't have any concave parts, then that methodology will work. And even if you do have polygons that have concave parts, like a crescent moon shape where it's hollow in here and it goes around like that, there's still some really good collision tests you can do with that by decomposing the polygon into just a bunch of triangles and testing all of the triangles. And there are also ways, again, to make those techniques faster by, rather than checking all the triangles every time, you do a bounding box test first. And again, if that fails and says they're colliding, then you go in and say, are they really colliding, by checking all the triangles. So most of the time it'll be fast, 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 fast as the things are far apart. But when they get near each other, you go, oh, now I got to spend a little more time being careful with these. So we're not going to get into the rest of those today, but I did want you to be exposed to some of those ideas. And like I said, I wanted to keep this lecture short today. I think we're going to come in right about 30 minutes, which is what my target was. And we might look at some of those more complex ones and spend a little time on polygon versus polygon collision, circle versus line, line segment versus line segment. But if we do, that'll be a future lecture. If your game, however, does need one of those kinds of collision tests, send me an email, shoot me a text message, get a hold of me, let me know, and I'll be sure to put that on one of the future lectures. Okay, so that's it for today. Go and work on your projects as a quick kind of fun thing, just to show that this stuff works. Here, let me switch over to the code where I implemented a few of these just for fun. Let me switch over so you can see that. So here's the code where I implemented point, circle, rectangle, rectangle, and circle, rectangle. And I did it the way that we said, and I threw together this little program, about 10 minutes worth of program. And I need to fix something. Hold on one second. apparently did not have this in a position where it was ready to show. Let me fix one thing. I changed the name of one of the functions. All right, let's try that. Guess I should have tested this before I decided to just start doing stuff with it. Oh, I still have it wrong. What did I call the function? Circle underscore rectangle. Circle underscore rectangle. All right, let's try it one more time. One more time for the people. All right, here we go. So there I have my circle, my rectangle, and I made this so when I click the left click the mouse, I can drag the circle around. And then I also made it so that will change color when it detects a collision happening. So if I'm grabbing that circle, notice it's gray. As soon as I touch that square, it turns red. And again, this is, even though that circle geometry is kind of irregular, this is a really fast collision test because primarily it's doing bounding box around the circle. It only has to do the other tests to handle those corner situations. Okay, so let's go back to the presentation for just a second. And like I said, that was all we were going to cover today. So everybody stay safe, work on your projects, and let me know if you need help or having trouble. And I will try to help you as much as I can. We're coming down to the final stretch here. We've got a couple weeks left. I have a couple more of these lectures that I want to put in front of you. And then the final week, the last regularly scheduled class day, which would be, what day is that? Wednesday. Right before finals week, that's when you're going to do your project presentations, and then we'll have the final in person during finals week. So I will also post a study outline, study guide for you to be prepared for what we're going to do on the final, what's going to be covered on the final. Make sure you've watched all the lecture videos, and also do focus on getting your project done because you also have to have the report done for that. And the report for that is going to be just kind of a summary. I'll post the requirements for that next week or maybe next class. We'll see. All right, so that's it for today. Everybody stay safe, and I'll see you soon. Let me know if you have questions. Bye.